Most of the comets that ever existed have never come anywhere near the Sun. They spend billions of years in deep freeze, orbiting so far away that sunlight is just a distant idea rather than a warmth you can feel. To understand where comets come from, we have to enlarge the solar system in our minds by a factor of 100, then 1,000, then 10,000. The familiar planets fit into a region about 30 astronomical units across. An astronomical unit being the average distance from Earth to the Sun, about 150 million kilometers. But comet country extends from just beyond Neptune at about 30 ATU all the way out to distances of tens of thousands of AU, where the Sun is no brighter than an ordinary star in the sky. The first comet reservoir is the Kuiper Belt, a vast, flattened ring of icy bodies beyond Neptune, roughly from 30 to about 50 astronomical units from the Sun. If the main asteroid belt is like crumbs under the table, the Kuiper Belt is the forgotten outer pantry. Hundreds of thousands of objects larger than 100 kilometers across, mostly mixtures of rock and ices like water, methane, and nitrogen. Many of these are stable residents, like Pluto and Eris, but some objects follow orbits that cross or skirt Neptune's path. Over millions of years, tiny gravitational nudges from that giant planet can slowly distort their trajectories, pulling them into more elongated paths that dip toward the inner solar system. This is how we get many short-period comets, the ones that return frequently, with orbital periods of under 200 years. Halley's Comet, with its 76-year cycle, is a famous example. Short period doesn't necessarily mean born nearby, but it does mean their orbits are compact enough to be shaped efficiently by the planets. Mathematically, their paths are ellipses tilted not too far from the plane of the planets, and their aphelia, their farthest points from the Sun, tend to sit in the outer planetary region or the Kuiper Belt itself. In effect, they are icy migrants that have been captured into predictable, repeatable routes by the combined gravity of the Sun and the giant planets. Far beyond the Kuiper Belt lies something stranger, the Oort Cloud, a hypothetical but strongly supported comet reservoir extending from perhaps 2,000 HIU out to 50,000 HIU or more. At those distances, the Sun's gravitational grip is incredibly weak. A gentle push is enough to reshape an orbit. The Oort Cloud is thought to be a roughly spherical swarm of trillions of icy bodies, each a few kilometers across, left over from the early solar system. Computer simulations suggest many of them started much closer to the Sun, among the giant planets, but were flung outward by gravitational slingshot interactions until they ended up in these enormous, slow, loosely bound orbits. Because these Oort Cloud orbits are so fragile, they are easily perturbed. A passing star, a light year away, or even the collective tidal gravity of the Milky Way's disk can slightly tilt or stretch an object's path. Over millions of years, a tiny change in direction can transform a nearly circular, distant orbit into an extremely elongated ellipse that dives toward the Sun. When that happens, an Oort Cloud body becomes a long-period comet with orbital periods of thousands or even millions of years, often arriving from random directions in the sky, not confined to the planetary plane. By the time we see such a comet blazing in our inner solar system, we are witnessing a brief, spectacular interruption in an otherwise unimaginably slow, cold journey that spans almost the full scale of our Sun's gravitational influence. So, every comet's path carries a kind of return address. Its orbital period, its inclination, and its shape tell us whether it likely emerged from the Kuiper Belt's icy ring or the Oort Cloud's distant shell. But knowing where they start is only half the story. The real drama begins when these frozen relics finally fall toward the Sun and begin to wake up.